At the forefront of intelligent progress is the European Council for Nuclear Research, CERN, esteemed for its significant contributions to atomic material science. This globally renowned atomic material science research center has recently unveiled an extraordinary finding from its massive Hadron Collider that could fundamentally alter our understanding of the universe. Scientists acknowledge that these surprising discoveries could reveal the presence of extraterrestrial life in a parallel reality. This groundbreaking idea has sparked excitement and serious debate among experts. Could this astonishing revelation reshape how we interpret the universe? Moreover, if confirmed, what critical insights will this discovery offer into the nature of reality itself? Join us as we delve into the recently published revelations, exploring how CERN scientists are breaking their silence on this chilling new discovery that has the potential to transform everything we know. The European Organization for Nuclear Research, also known as CERN, has been renowned for its daring experiments since its inception in the 1950s. While it has often been at the forefront for good reasons, its experiments have also raised concerns about the potential creation of black holes, cracks in our existence, and other dangers. One of CERN's most notable and controversial achievements was the development of the Large Hadron Collider (LHC). The LHC is the world's largest particle accelerator, officially launched on September 10, 2008, and remains the latest addition to CERN's accelerator complex. Spanning more than 27 kilometers of superconducting magnets and accelerating devices, the CERN Super Collider cost over $4.5 billion. Many argue that this money was well spent, as the LHC has led to some of the most significant discoveries of the past few decades, such as the identification of the Higgs boson and various previously unknown particles. This colossal machine accelerates particles around a circular track at nearly the speed of light, completing more than 11,000 laps. It achieves this through a series of powerful electromagnets that generate magnetic fields almost 100 times stronger than Earth's. Some have expressed concerns about the effects of creating such intense magnetic fields on nearby devices and their impact on Earth's magnetic field. Once these particles reach their maximum speed, they collide head-on at incredible energy levels, producing a variety of particles. These collisions release a torrent of particles, most of which exist for only fractions of a second before disappearing. By altering the source of particles, scientists can uncover new particles. At these collision sites, highly sensitive detectors record vast amounts of data, amounting to more than 15 petabytes annually. To put this into perspective, 1 petabyte is equivalent to approximately 250,000 movies. In 2017, the LHC achieved a significant milestone by permanently storing over 200 petabytes of data in its tape libraries. But what exactly are they looking for in this data? Scientists identified anomalies involving a specific type of particle known as a beauty quark. Quarks are fundamental building blocks of matter and come in various flavors. Some of these flavors are highly unstable, decaying into other particles in the blink of an eye. The beauty quark, with an average lifespan of 1.2 trillionths of a second, became the focus of attention due to unexpected behavior. Its decay pattern differed from what researchers had predicted based on the standard model. When a beauty quark decays, it interacts with the weak force and transforms into a pair of lighter particles called leptons, either an electron or a muon. The standard model predicts a 50-50 chance for each particle. However, LHC data revealed that beauty quarks decayed into muons 70% of the time instead of electrons. This anomaly suggests the potential involvement of a previously unknown particle in the process. This has led some researchers to speculate that new physics might be at play. The discovery of a new force-carrying particle could extend the standard model, answering long-standing questions and introducing new mysteries. The standard model explains 3 fundamental forces: electromagnetic, strong, and weak forces. However, it does not account for gravity or dark matter, the universe's most abundant form of matter. Recently, researchers observed another irregularity that diverged from the standard model's predictions, prompting further investigation. Could this new force help explain these anomalies? Scientists have proposed the existence of a hypothetical particle called the Z-prime boson. This force-carrying particle, though weak, may interact uniquely with electrons and muons. If confirmed, this discovery could revolutionize physics, shedding light on unresolved mysteries like the nature of dark matter and the role of the Higgs boson. As Elon Musk noted, CERN constructed the largest and most powerful particle collider in human history, the LHC, between 1998 and 2008. Over 10,000 scientists, numerous organizations, and labs from more than 100 countries contributed to this project. The LHC is situated in a 27-kilometer tunnel on the border between France and Switzerland, approximately 175 meters underground. The LHC's first recorded collision had an energy of 3.5 tera-electron volts (TeV) per beam, breaking previous world records. Its energy levels were later increased to 6.5 TeV per beam following upgrades. This remarkable machine accelerates proton beams, and for a limited period each year, lead beams, to test various hypotheses in particle physics. The LHC's primary goal is to study the properties of the Higgs boson and search for a wide array of new particles predicted by subatomic theories. Hadrons, composite subatomic particles made of quarks, are bound together by the strong force, much like atoms are held together by electromagnetic forces. Protons and neutrons are two examples of hadrons. They are essential components of atomic nuclei, making them fundamental to the structure of matter. By accelerating and colliding these particles at incredibly high speeds, researchers aim to recreate conditions similar to those just after the Big Bang. This allows scientists to explore the fundamental forces and particles that govern our universe. One of the most famous discoveries made by the LHC was the confirmation of the Higgs boson in 2012. Often referred to as the God particle, the Higgs boson is a crucial element of the Standard Model. It is responsible for giving mass to other particles through its interaction with the Higgs field. Without the Higgs boson, particles would have no mass, and the universe as we know it could not exist. While the discovery of the Higgs boson was a monumental achievement, it raised new questions. Why does the Higgs boson itself have mass? How does it interact with dark matter? These mysteries have driven further experiments at the LHC, pushing the boundaries of particle physics. The potential discovery of the Z-prime boson could address some of these unanswered questions. As a force-carrying particle, it may represent an entirely new force of nature. If confirmed, this force could unify the known forces of the Standard Model with gravity, bringing us closer to a theory of everything that explains all physical phenomena. However, such breakthroughs are not without controversy. Critics argue that the immense energy and scale of the LHC experiments pose potential risks. Concerns about creating microscopic black holes or destabilizing the fabric of spacetime have been raised, though scientists have consistently assured the public that these risks are negligible. Despite these concerns, CERN's experiments continue to capture the imagination of scientists and the public alike. The possibility of uncovering new dimensions, understanding dark matter, or discovering the origins of the universe fuels the ongoing work at the LHC. In addition to its groundbreaking research, CERN has also made significant contributions to technology and innovation. The World Wide Web, for example, was invented at CERN in 1989 by Tim Berners-Lee to facilitate data sharing among researchers. The technological advancements driven by CERN's experiments have found applications in medicine, computing, and engineering, benefiting society in countless ways. As we look to the future, the potential discoveries from CERN's research hold the promise of transforming our understanding of the universe. Whether it's identifying new particles, unlocking the secrets of dark matter, or developing a unified theory of physics, the work being done at CERN represents the cutting edge of human curiosity and ingenuity. Stay tuned as we continue to explore the latest developments from CERN and the implications they may have for science, technology, and our understanding of existence itself. Hadrons that are generally perceived include the pions and kaons, which were first found in enormous beam tests in the late 1940s and mid-1950s. The LHC brings two impacting particle beams together so they can collide. The Higgs boson is believed to be a key particle related to the Higgs field. It is the quantum excitation of this field, similar to how you notice waves in the sea. The boson is like a new species in the particle zoo. It needs the quantum qualities of key matter, as well as the carriers of quantum interactions like electromagnetic force, weak force, and nuclear interactions. The Higgs boson was found at the Large Hadron Collider, a historic discovery achieved all the while by the two major multifunctional experiments, ATLAS and CMS. It was declared on July 4, 2012 at CERN. At the time, the new scalar boson was found primarily in two rare decay channels that gave the clearest signals, decaying into a pair of photons, which required a completely quantum virtual cycle, and decaying into a pair of Z bosons, the carrier of the neutral-weak interaction. Although the discovery of the Higgs boson at the time confirmed the Standard Model, research into this elusive particle did not end there. One of the major discoveries since 2012 was the confirmation of Higgs decays. According to CERN, the study of this elusive particle will continue to evolve during the LHC's third cycle, especially once the Atom Smasher's high luminosity upgrade is finished in 2029. This will allow the LHC to conduct more collisions, giving researchers a greater opportunity to identify unusual physics, for example, events that don't fit into the Standard Model. CERN estimates that when the accelerator is upgraded every year, it will produce 15 million of these particles, compared to the LHC's production of 3 million Higgs bosons in 2017. This may help recognize various types of Higgs boson theories that go beyond the Standard Model of particle physics, predicting up to 5 distinct kinds of Higgs bosons, some of which may be produced less frequently than the primary Higgs. Even before the upgrades, researchers have provided conclusive evidence for a magnetic Higgs boson. Yet what difference does this make? The Higgs field was tremendously important in the early times following the universe's creation. It governs the very nature of the vacuum that exists in our space-time. It allows matter and interactions to exist as we know them, as well as the development of mass in known fundamental particles. Without the Higgs field, and consequently the Higgs boson, the universe would lack nuclear particles, stars, and life. Why do you think the Higgs boson is known as the God particle? Well, the media helped cement the Higgs boson moniker, the God particle, after its discovery. It is most frequently traced back to Nobel Prize-winning physicist Leon Lederman, who, out of frustration, referred to the Higgs boson as the goddamn particle because it was so hard to detect. According to Business Insider, when Lederman wrote a book about the Higgs boson in the 1990s, he wanted the title The Goddamn Particle. However, the publishers disagreed and changed it to The God Particle. That was the beginning of an issue between particle physics and religion that continues to concern modern physicists. Nevertheless, it is difficult to underestimate the importance of the Higgs boson and the Higgs field, as only particles would have mass under this aspect of nature. This suggests there would be no stars, planets, or people, which helps explain its provocative moniker. Apart from the clear need to describe the new particle, researchers continue to investigate the Higgs boson for two reasons. First, they want to understand how the very vacuum we live in began in the early universe. Second, they want to know how this vacuum can remain stable. The Higgs field is unique in that it imparts non-zero, mean expected potential energy to the vacuum itself. This has a significant effect on our universe. Scientists believe that understanding the structure of this energy potential is responsible for the existence of electromagnetic force with infinite reach and weak force with a very short reach. To do this, researchers need to explore how Higgs bosons interact with one another. Additionally, they need to create pairs of Higgs bosons. The Higgs boson contributes to answering the fundamental question of how all other major particles obtain their mass. Its mass, however, remains unexplained. Any discrepancy in the theory does not account for this mass and causes potential instability. Quantum fluctuations could disrupt the vacuum itself. Fortunately, this happens on time scales much greater than the known lifetime of the universe. Still, researchers are actively searching for additional Higgs boson-like particles that could indicate the presence of new physics required to stabilize the Higgs boson mass. All these considerations fuel the study of much more data, and if possible, access to greater collider energy. For this reason, 10 years later, many researchers worldwide remain focused on the work. The Higgs boson was first proposed in 1964 and discovered in 2012. Scientists have questioned why it took so long. This is because the Higgs boson is both large and extraordinarily unstable. To create such a massive particle, researchers had to focus a tremendous amount of energy in a small space. They needed a high-energy collider. Once formed, Higgs particles decay in various ways, with only a small fraction detectable from the background. Scientists built the largest and most complex detectors to identify such particles. Then, they analyzed millions of particle collisions to find a Higgs boson signature. At any rate, will CERN's activities and discoveries lead us to immense revelations? Will it send us to our ultimate end? Researchers have three main hypotheses about what CERN is doing. The first and most alarming idea, which has drawn some attention, is that the organization is attempting to open a doorway to hell. Some believe that CERN's experiments with subatomic particles traveling at the speed of light will push humanity past the gates of hell. The second hypothesis is that CERN's research could lead to breakthroughs in understanding the fabric of our universe, including the potential discovery of new dimensions or realms beyond our own. Some theorize that the collider could help explain the mysteries of dark matter, dark energy, and the very nature of space-time. If the LHC's experiments can uncover these hidden elements, it could transform our understanding of the cosmos in ways we cannot yet fully imagine. The third and perhaps most optimistic theory is that the advancements at CERN might lead to technologies that revolutionize various industries. The creation of particle accelerators has already had some unintended but profound benefits, including advancements in medical imaging, cancer treatment, and materials science. With further research into the Higgs boson and other fundamental particles, there could be future breakthroughs that affect everything from computing power to energy efficiency, improving life on Earth in ways we haven't yet realized. Despite these possibilities, the debate surrounding CERN and its experiments continues to spark controversy, with some critics warning that the consequences of unlocking unknown forces might be too dangerous to predict. As scientists push the boundaries of particle physics, they tread a fine line between expanding human knowledge and encountering the unknown, an unknown that might have consequences beyond their control. Regardless of the outcomes, the search for answers continues, driven by a fundamental desire to understand the universe at its most basic level. From the discovery of the Higgs boson to the ongoing research into its properties, scientists at CERN and other research institutions are not only challenging our current understanding of physics, but are also raising profound questions about the very nature of existence itself. Whether their work will ultimately lead to a more harmonious understanding of the universe or unlock dangerous forces remains to be seen. But one thing is certain: the pursuit of knowledge is an unrelenting force in itself, pushing humanity to reach beyond the stars and into the deepest mysteries of space, time, and matter.